In today's video, we are going to talk about how the deep neural networks are trained. We have by now discussed the basic structure of the deep neural networks. So we start with a fixed architecture of DNN. That is, we fix the set of vertices or nodes, the set of edges, which node is connected to which node in the network, and the activation function that we are going to use at the hidden layers. What needs to be done is to fix the weights to attach to the edges. So in other words, the weight set W needs to be learned. This will be learned from the training set S, which consists of x1, y1 up to xn, yn. Xi's are the observations, for example, the images. Yi is the label corresponding to image or observation xi. Yi belongs to 1 to n in case it is a classification problem. In this case, there will be n classes, or yi is a vector with dimension rm prime if it is a regression problem. In training, what we need to do is we need to find W, which will minimize the empirical risk. For a given W, empirical risk, which we are denoting by LSW, is 1 by n sigma L FW xi yi, where L is the loss function, FW is the input-output map for a given W. So FW xi is the output of the network if we have fixed the weights W and the input is xi. We compare that to the actual label yi corresponding to xi in the training set. And then LSW is the empirical risk for corresponding to this W. And what we need to do is minimize this and find the W which will minimize the empirical risk. The loss function L depends on the application, and we have discussed that earlier. If it is whether it is a classification problem or it is a regression problem. Instead of minimizing empirical risk, we could minimize the regularized empirical risk. That is, take this empirical risk and add to that another term, lambda norm of W square, where lambda is a positive quantity. Based on solving the above optimization problem, either optimizing the empirical risk or the regularized empirical risk, the optimal solution we denote by W star, which we will find out using the algorithms that we are going to use or in this video. And given this W star that we are going to get, it is, of course, going to be a function of the sample training sample S. The corresponding empirical loss for this W star we are going to denote as LSW. The generalization loss for this we are denoting by LDW star. That is the expected value of the loss corresponding to W star, where the expectation is taken with respect to the distribution of xy, and which we are denoting by D. This is, as we have discussed earlier, the loss that the neural network after training will experience in the field when it is deployed outside. This we are going to denote as LDW star. If the expected value, remember, LDW star is still a function of S. If we take expectation over S of LDW star, This is the expected value, take an expectation or the sample size. If expected value ES of the generalization loss at W star is greater than expected value of the empirical loss at W star, then we call it a overfitting problem. If lambda is small, lambda that we have used in the regularization function, then we will expect overfitting. If it is large, then we can expect underfitting, and therefore we should choose a moderate lambda because we don't want underfitting or overfitting. Now, to find this optimal point, W star, there are many optimization algorithms that have been proposed in literature. The most common are gradient descent, which we denote by GD, stochastic gradient descent, and refinements further. There are many refinements of stochastic gradient descent that have been proposed in recent literature. Some of them we are going to discuss in this video. Gradient descent algorithm is the classical algorithm used for optimization. It is used to minimize any function from RD to R. The function should be, of course, differentiable. The algorithm works as follows. You start with some initial condition x naught, and you run the iterative algorithm xk is equal to xk minus 1 minus eta gradient of f at xk minus 1. You run this iteration from k is equal to 1 to t that you fix. At the end of running the algorithm, you calculate the average of points x1 to xk, and we denote that by x bar. This is the final point that we obtain after running the algorithm, and the aim was to get the optimal point x star. We approximate that by x bar. If capital T is large, we'll expect that x bar will be close to x star. If function f that we are minimizing is convex, the definition of convexity is f alpha x plus 1 minus alpha x prime less than equal to alpha fx plus 1 minus alpha fx prime for all x and x prime, and for all alpha between 0 and 1, then that function is called convex. And in that case, the x star that we have shown in the previous slide, that the limit point of the gradient descent algorithm, that will be a global minimum. What that means is that at this point x star, a function f is less than equal to fx for any other point x. If the function is not convex but differentiable, in that case, the x star that we are going to obtain from gradient descent algorithm satisfy a property called local minimum. What it means is that at this point x star, function fx star is less than equal to fx for all point x in a neighborhood of x star. Okay? By neighborhood, we mean by norm between x star and x. Difference of norm in x star and x is less than epsilon for some epsilon greater than 0. For the general case that we have discussed above, there can be multiple minima. Of course, even at convex scan, there can be multiple minima, but all those minima in case of convex will have the same value. In the general case, when the function is not necessarily convex, there can be multiple minima. And we are showing one such case here in this picture. We have plotted fx. This function that we have plotted is not a convex function. For this function, there are multiple points x1 star, x2 star, x3 star, at which locally the function value is minimum around this point, like x1 star around this point, its value is minimum. Same way here and here. But x1 and x3 are local minimum, while x2 star is a global minimum. Because at this point, the function value is minimum over whatever we have reason of constraint here. As we mentioned, for the general function, gradient descent may converge to a local minimum and not necessarily to the global minimum, which is x2 star. So in this case, for example, it could converge to x1 star or x2 star or x3 star. It depends on which one it converges on the initial point x0 where the algorithm starts. If the algorithm starts somewhere here, it will converge to x1 star. If the algorithm starts x0 is at somewhere here, then it will converge to the global minimum. If it starts here, then it will converge to this. So in the general case, what you will do is you can you can run the algorithm, gradient descent, multiple times from different initial points x0, and depending upon where it starts, it might converge to one of these points. You can try, for example, let's say you try from 10 different x0 points, and it may converge to 10 local minima. Some of them may be same. And then among them, you pick the point at which the function is minimum. So if you try 10 times, you will get 10 minima. And among those 10 minimum, pick the minimum at which f is minimum among these 10. And that f star, x star, you are going to choose. So this is how we generally handle general functions if we want to minimize them by gradient descent. Stochastic gradient descent is somewhat like gradient descent. And there also, we start with some x0 and we iterate. Xk is equal to xk minus 1 minus eta vk minus 1. Remember, the difference here is instead of gradient of f at xk minus 1 here, we choose some vk minus 1, where vk minus 1 is such that expected value of vk minus 1 given xk minus 1 is equal to the gradient of the function at xk minus 1. Remember, for gradient descent, at this point, we choose this term itself, but in stochastic gradient descent, you have some possible choices. So vk minus 1, which should satisfy this. After t steps, so you decided to run the algorithm for t steps. Again, you can take an average of all these xk points to get xk, which you will take as an approximation of the minimum point. Now, so this gradient descent and stochastic gradient descent, we have right now described for a general function f. We are going to, since in our case, we are interested in finding a W star which minimizes the empirical risk. We apply GD and SGD for that particular problem. The empirical risk is LSW based on the loss function L and x1, y1 to xn, yn, the training sequence. So this is what we call empirical risk. We may want to minimize this, or we may want to minimize the regularized empirical risk. If L, this loss function L, and FW, remember FW is the input-out mapping of the neural network for given W set. If both of these are convex, then LS is convex. And in that case, this regularized loss is also convex because this is a convex term. But in deep neural networks, FWX is not convex. So even if L is convex, the overall function LSW is not convex, and this is a major problem in training deep neural networks. Therefore, whenever we are going to use GD or stochastic gradient descent, we can expect only a local minimum, which can in general be utterly bad, as we have seen in the picture. So X1 star and X3 star, what had the value at those function at those points much higher than the value at Fx2 star, which was the global minimum. So now we apply gradient descent on if minimizing the empirical risk of the process. So this is the iteration. You start at some W0 and you iteratively calculate Wk, k is equal to 1, 2, 3, and so on, up to let's say capital T. This is the gradient descent iteration. Wk is equal to Wk minus 1 minus eta. Eta is some positive constant, and gradient of Ls with respect to W at point Wk minus 1. Remember, Ls is empirical risk. This is average of the risk or loss at all the points, training points there. To evaluate this function, the summation of n variables like this, we will have to compute gradient of W with respect to this loss function n times, where n is the number of training sequence. And in general, in deep neural networks, n will be very large. And therefore, for each of this step, computing this step is computationally very expensive if we want to use gradient descent algorithm to solve this empirical risk optimization problem. And in fact, in case if you want to use regularized risk, then again, this term certainly will be there. So the computational cost will be of the same order. If we apply stochastic gradient descent, again, this step is similar, but remember, there Wk is equal to Wk minus 1 minus eta. There will be a Vk here. Vk is such that expected value, Vk minus 1 will be here. Vk minus 1 is such that expected value of Vk minus 1 given Wk minus 1 is this gradient, overall gradient with respect to the capital L. We can show that taking this term, where we are taking gradient with respect to the loss at a single point xy, where xy we have randomly picked from the sample as training sequence. Then this will satisfy the condition of Vk minus 1. So therefore, for stochastic gradient descent, at each step, we have to take a gradient of this term only once, as against in the gradient descent, you have to take gradient with respect to this. You have to take at each step gradient of this term n times. So therefore, stochastic gradient descent is computationally far, far less expensive than gradient descent. And in fact, using gradient descent the way it is in training neural networks is practically not feasible. And there is one more important property of stochastic gradient descent, and that is stochastic gradient descent does not minimize empirical risk only, which is done by the gradient descent. It in fact minimizes expected value of the empirical risk. In other words, it minimizes the loss in the field, which is what is of actual interest to us. So therefore, stochastic gradient descent has two important properties. One is at each step is computationally far more uh, inexpensive compared to the gradient descent, and it minimizes the actual function of interest instead of LSW, which is done by the gradient descent. So you would say, well, great. I mean, as stochastic gradient descent does the job that we really want to do. However, in practice, it so turns out that if you apply the stochastic gradient descent algorithm on problems of interest, it doesn't really converge very well because the term that we have used here, this term, we are taking the gradient only at one point xy in out of the n samples here. This is very noisy. This term is very noisy. And if you see in practice, if you do the simulations or any other way, that in fact the stochastic gradient descent does not really converge well. Therefore, people have suggested modifications to it. And the main modification is instead of taking gradient at only one point xy from the sample, you take gradient with respect to W of the loss at a batch, mini batch, bk out of S. For example, suppose the training sequence has 1,000 points. Out of those 1,000 points, I could take 10 points randomly and use gradient at those 10 points. So BK has 10 points from the sampling training sample here. And instead of using gradient only at one point, you take gradient at those points and divide by the number of elements in the mini batch. So in other words, you take the gradient, which is the average of the gradient at multiple points. Also, the eta, the constant term that we have used in gradient descent, stochastic gradient descent, we vary it with the k, the in WK, the k point that we have. With k, as you are running the algorithm, eta k is reduced, and we can take it like some eta, positive constant, divided by k raised by alpha, where alpha is equal to 1 or 0.5. That means as k increases, the sample of WK that we are taking, as the algorithm is developing, the constant eta is being decreased. So this is called mini batch stochastic gradient descent algorithm. And in practice, it works better than stochastic gradient descent because, as we said, stochastic gradient descent in general may not actually converge. It's just too noisy. So this algorithm, you can think of some compromise between gradient descent and stochastic gradient descent. In gradient descent, at each step of the algorithm, at each iteration of the algorithm, you are taking gradient of this function at all points x1, y1 to xn, yn. In case of stochastic gradient descent, you are computing this only at one point randomly picked from this n samples, but that doesn't work very well. So you take gradient at a batch, small mini batch from S, and take an average of that. So this works much better than the stochastic gradient descent. But since BK is a small number of sample from S, the computational cost is still much less than the gradient descent, and it's not as noisy as gradient descent. So this is certainly an improvement over stochastic gradient descent, but over time, people have discovered improvements over this. And because this is the algorithm which uh, people are using for training neural networks, so it's very, very important that we come up with improvements on this basic idea. So as I said, mini batch is first step in that direction. Another improvement over this is what is called momentum method. Remember, Vk is what we are going to use. Vk, so Wk plus 1 is going to be equal to Vk minus Wk minus Vk. Here, Vk is going to be changed compared to the mini batch. In mini batch, you take average of the gradient of loss at Wk minus 1. In this case, we are writing Wk at a certain mini batch. Now you take that Gk and define Vk as equal to gamma Vk minus 1 plus eta k Gk. Eta k is non-negative constant. Gamma is also a small constant. And then instead of using Gk of mini batch, you use this Vk, and the algorithm now is written as Wk plus 1 is equal to Wk minus Vk. If I take this gamma, so gamma is going to be between 0 and 1. If I take this gamma to be 0, then because this Gk is the term that we have here, so this we are denoting by Gk. For gamma is equal to 0, this momentum method will become same as mini batch. This method does better than mini batch. In the beginning of the algorithm, it accelerates convergence to the optimal point, W star, and also it helps in escaping local minima. Remember the function that we are minimizing here for the deep neural networks in not is not a convex function. Therefore, GD or SGD or mini batch, they are all going to converge to local minima. But this modification that we have given here helps escape the algorithm from some of the local minima. So this is certainly a good advantage. And of course, it's accelerating the convergence here as well. After the momentum method, there are many other methods that have been proposed. Till now, this constant eta k in the iteration, initially it was constant equal to eta. Then we changed it from eta to eta k, which is changing with iteration k and going down as k increases. But now we change this because wk is a vector. We change eta k to a vector eta k. That means eta k also has dimension d, dimension of wk. And there are advantages of doing that because if we take scalar eta k, then in wk, you are writing wk is equal to wk minus 1 minus eta gradient. So the change in wk for all components is happening at the same rate. But if we change that to vector w eta k, so that different components will be multiplied by different constants here. If this constant is larger, then the difference for that component in wk will be larger. And if it is smaller, then it will be smaller. So we can modify it, and based on this idea, many algorithms have been proposed. These are called ADAGRAD, RMS prop, ADAM, and so on. So Adam is among these the latest, and it does certainly better than all these other algorithms that we have shown. So it's better than Algrad, it's better than mini batch and momentum and so on. So that's the algorithm that we give now. Remember, final iteration is going to be WK plus 1 is equal to WK minus some quantity here. Earlier it was VK. Now we are writing it as GK prime. This is a vector. And at iteration K, we obtained this by all these equations given here. We start with VK. We define a sequence VK. It can start with V0 is equal to 0. And then VK is equal to beta 1, VK minus 1 plus 1 minus beta 1. GK, beta 1 is a constant. It can be close to maybe 0.99. And SK is another sequence we define these. So this is SK is equal to beta 2, SK minus 1 plus 1 minus beta 2, GK. And this is notation which we describe now. So this is vector GK multiplied with this operation, circular operation GK. And this is defined as if GK is the vector with components A1 to AD, then GK circle GK is actually component-wise, each one of them is made square. A1 square up to AD square transpose. So SK is defined this way. Then from VK and SK, we define VK's hat equal to VK divided by 1 minus beta 1K raised to power K. And SK hat is SK divided by 1 minus beta 2 raised to power K. From VK hat and SK hat, now finally we define GK prime J component for each component J, component-wise from the components of VK hat and SK hat. And finally, we get WK plus 1 is equal to WK minus GK prime. As we said, that Adam algorithm, which was invented in around 2016, works very well. There have been improvements over Adam in later years also, because it's a very, very important algorithm to work with. But Adam is considered pretty good and is being used very often in training of deep neural networks. So in this lecture, we have explained the different algorithms for training deep neural networks. And we will continue further on the architectures of deep neural networks in later videos in this course. Thank you very much.